Welcome to the world of electrostatic potential. Now, I know what you're thinking. There are so many electric blanks, electric forces, electric fields, electric potential difference. There are so many electric insert other noun phrases in this course that it's hard to really separate them. This chapter, at the end, I plan on making that very clear. What is the actual difference between all these different concepts we're learning right now? Okay? But for now, all I'm going to say is that electric potential is the other side of the electric field coin. Okay? So let's say we have this coin, we have heads and tails. Okay? And on top, the heads, we have electric fields. That's one way of explaining why objects move at a distance when there's charged particles that are near each other. All right. So electric fields, remember, there's a particle that creates a field in all of space, and then if you drop another charged particle inside of that field, then the field and the particle interact so that the particle starts moving. So that explains why these two charges are having an effect on each other at some distance. Now, electric potential is another way of explaining why a charge that's next to another charge will actually move, right? And the reason is because the potential here and the potential here are different. And just like a ball will roll from one height to a different height, a charged particle will roll from one potential to another potential. And that potential difference is, for example, what we talk about when we talk about the voltage of a battery, right? One end of a 9-volt battery is at 9 volts. The other end is at 0 volts. So the electrons roll down the 9 volts all the way to the 0 volts of the battery. And so this is what we're going to explore this week. For the quote of the week, this one's very special to me. I think it's very, very important because this psychologist, Marshall Rosenberg, invented an entire way of communicating called nonviolent communication. And anyone who has ever struggled in a conversation with someone before should look this up. Because it's very powerful, and honestly, I'm not going to lie, I think it changed my life. And so one of the things that Marshall Rosenberg says is that all evils that humans do in the world are really expressions of unmet needs. All right? And so what he's saying is that instead of us living in a world where everything's good and evil, there's good people and there's bad people, right? What it comes down to is that human beings all have needs. And if those needs aren't met, people are going to try to meet those needs in different ways. Some of those ways can be very, very toxic, like, deceit, like crime, like hurting others, like infidelity, right? There are all these different crimes or different, ills of society, things that hurt us, that are really not because there's some people that are good and bad, but really because we're all trying to meet these needs that we have as human beings. And some of the strategies that we use to meet those needs are productive to us living fulfilled lives. And some of those strategies to meet needs are very toxic. And so the evils of the world are really bad strategies to meet the needs that we all have. And I think that's just nicer than looking at the world as everyone's good and the rest of us are evil, So think about that. If you're interested, just Google Marshall Rosenberg or nonviolent communication, and you'll learn a lot. If you're curious, reach out to me. Let's go to why do we care? Why do we care about electric potential? Okay, there is something that's happening right now in my brain and all of your brains, trillions of times a millisecond, and that is action potentials in neurons, right? In other words, a certain potential difference between the inside and the outside of your neurons is building up, right? And when that builds up to a high enough difference, there is an influx of ions into the neuron, right? The axon of the neuron. It travels along the axon, and then that allows an electric potential to happen in the next neuron, and this is how the neurons communicate with each other. This is happening literally trillions of times a second. And so, again, if that's not important or valuable to understanding human biology and human psychology, then I don't know what is. So in this chapter, we are going to be learning a lot more about how those action potentials develop, and what the heck is a potential difference anyways, and why does one arise between the inside and the outside of a neuron. Okay? I want to start out by looking at electric potential energy. Okay? Two different things. I know it's weird, I know it's annoying, but electric potential energy is just potential energy. All right? It's in the gravitational world, we know that if we have, the ground, right, and then we have a ball somewhere above the ground, then you have gravity, right, a force of gravity or a weight that's pulling it down, right? And that by having a certain height, this particle, this ball, has a potential energy, a gravitational potential energy of its mass times the acceleration due to gravity on whatever planet you're on, times the height of that ball, okay? And this is measured in joules, remember. Okay, so remember, this potential energy then can be converted into kinetic energy, and then the ball starts to accelerate. And down here, then you have all this kinetic energy, and there's this high speed, right? Potential energy goes down, kinetic energy goes up. And that's why, if ball falls on you, it hurts, right? Or, you can, hit the ground and bounce, right? So, again, this is how we're combining the world that we had of last year, this world of energy, with this new world that we're dealing with electricity and electrostatics. So it turns out that in nature, wherever you see a force, you're going to see some energy, all right? And so if there's a gravitational force, there's going to be gravitational potential energy, right? And if there is an electric force, there's going to be an electric potential energy. So let's say that I have, instead of the air and the ground, I have two plates, okay? And I have a positive plate, and I have a negative plate, right? And let's say that I put a proton right here, okay? Again, just like that ball is going to want to fall down to the ground, this proton is going to be attracted to these negatives, and it's going to want to fall down, right? If you just blinded yourself to everything else and just looked at the objects, it almost looks like the same exact thing is happening, right? Only thing is one's happening due to the electric force, the other one's happening due to gravitational force, okay? So just like if you hold this ball here, it's going to have a potential energy of mgh. It turns out that if you hold this proton here, it is going to have a potential energy of the charge times the strength of the electric field, because remember, there's an electric field here going down, right, from positive to negative, positive to negative, positive to negative, okay, times the distance that it is away from the other plate, okay? So that's going to be your D. So basically, more accurate to say, how far is the particle from the other plate, okay? So there's a cool analogy here, right? If you translate the gravitational world to the electric world, it's as though H is like D, right? E is like gravitational acceleration, and the mass is like the charge, which kind of makes sense, right? So in many of the equations of gravity, you can replace your variables, these three variables, with the variables of the electrostatic world, with these corresponding variables over here. So I'm trying to point out and paint this picture of this. You're not learning anything that new, because it's just a new force, and the behavior's the same. You're just changing the characters of the story, okay? The new characters are distance, charge, and electric field. By the way, I should be more careful here. This is gravity. If these are all the gravitational variables, I should keep all the gravitational variables here. So gravity is like the electric field. Okay. All right. So once again, you're both dealing with forces. They both have a certain potential energy, but the characters of that story are changing. Okay? And so we can use conservation of energy just like we did over here to solve for the velocity when that ball falls, to find out what the velocity of this charged particle will be when it falls. And so let's do an example. If you guys could go to the slide that says conservation of energy in the electro world. All right, so I am going to imagine that I have two plates here. The plates are, you have a negative plate, and you have a positive plate. Okay, and we have a proton and an electron in here, and they're both like exactly halfway in between. Okay, now you know there's going to be a force on the proton in this direction, right? It'll be attracted to the negative plate, and there's going to be a force on the electron towards the positive plate, right? But they're both the same distance, a certain distance d away from each plate, okay? And so they're both going to have a certain potential energy, all right? So the question is, what is each particle's energy? And I'm going to start with the electron here, okay? So what is the particle's energy if it's at rest right now? Well, it's only going to be potential energy. And that potential energy, we learned, is going to be equal to E Q times D. Right? So what is the electric field? Well, remember, we know that the electric field due to a capacitor is equal to Q over epsilon 0 times D. All right. I'm going to erase this for now so that I can finish this problem. Right. We know this problem is telling us that each plate has 1 nanocoulomb. So that's going to be equal to 10 to the minus 9 coulombs all over epsilon, which is 8.85 times 10 to the minus 12, right? And, oh, sorry, this is not D, but this is A, the area of the plates, okay? But the area of the plates are, it's square. It says 2 centimeters by 2 centimeters parallel plate, right? So that's going to be 0.02 times 0.02. Right? A square, the area is side squared, or length by width, right? So that's going to be the area. And so then we can very easily calculate the electric field inside of here with a value of 2.8 times 10 to the 5 newtons per coulomb. Okay? All right, so we know the electric field in here, which, by the way, points in this direction. We know that electric field is going to be, I'm going to erase this up here because we don't really need this anymore. The electric field will be E equals 2.8 times 10 to the 5 newtons per coulomb. Pretty cool. Okay, once we have that, it's very easy to find the potential energy of that electron, which is, again, going to be Q E times D. What is the charge of an electron? Well, it's 1.6 times 10 to the minus 19. We know that. The electric field is 2.8 times 10 to the 5 times, what's the distance? Well, the distance, it says the spacing is 2 millimeters. Right? So if the whole thing is 2 millimeters, then these D's have to be 1 millimeter, or 0.001 meters, right? Okay, what do I get? I get that the potential energy of this electron is, in this space, 4.5 times 10 to the minus 17 joules. Very small, very low energy, but again, to be expected. It's a very small charge, okay? Now, get used to the fact that you guys have probably seen this and expected this and have noticed this already, but we have a situation where the exponents in this level of physics are often very high and very wonky. Don't let that scare you unless you have a speed that's higher than the speed of light. But otherwise, You can kind of expect that, okay? So that's our potential energy. Great. Good stuff. Good stuff. Okay. All right. We know the part of the energy of that electron. Let me ask you this. Is this energy going to change at all for the proton? No, it's got the same charge, it's in the same electric field, and it's the same distance. So this is the same for both particles. I'll put that right there, both particles. Okay? All right. Now, the next question is, what is each particle's speed as it reaches the plate? And this is where we get to use conservation of energy, which was so helpful last semester, and now we can use it to make our life easier this semester too, right? So we want to find out what is the velocity right there when this electron shoots over and reaches the other side of the plate. Okay, well, just like we would do before, we say that E1 equals E2, right? The energy here, E1, must equal the energy here, E2. Okay, well, what is the energy here in E1? Well, it's all potential energy. And in fact, we just calculated it. It is this potential energy, 4.5 times 10 to the minus 17. So we have 4.5 times 10 to the minus 17 joules equals, what's this kinetic energy over here? Well, it's going to be kinetic energy, right? So that's just 1/2 mv squared. And so we put over here 1/2 mv squared. All right, pretty cool. All I need to do is put in my mass for an electron, which remember is 9.1 times 10 to the minus 31 kilograms. Multiply by 2, divide by the mass, take the square root. Go ahead, pause if you need to, but instead of writing all that, because I don't have the space, I'm just going to say, after I put in my mass, after I solve for everything, take a square root, I get a velocity of 9.97 times 10 to the 6 meters per second. Tell me if I'm wrong, but that's what I'm getting, 9.97 times 10 to the 6. Once again, we do our check. Is this bigger than the speed of light? Pretty dang fast, but not bigger than the speed of light. That is an acceptable answer, okay? And if you want to ask yourself the question, what about for the proton? What changes? The only thing that changes is the mass of the proton changes. And remember, the mass of a proton is 1.67 times 10 to the minus 27, okay? Which means you can go ahead and solve for what the velocity of that proton would be by putting that mass there. You would expect the velocity to be bigger or smaller? A little bit smaller because the mass is bigger, okay? So go ahead and check that out on your own. And in the meantime, I hope you have appreciated the fact that just like in the gravitational world, there's potential energy in the electric world. And just like we could use conservation of energy to explain the velocity of an object in the future, we can use conservation of energy to find the velocity of an object in the future as well, using the electric potential energy. All right? Same world, different characters.